Billions and billions of galaxies. The universe is so vast, we can't even imagine what those numbers mean. But 14 billion years ago, none of it existed. Until the Big Bang.
The Big Bang is the origin of space and the origin of time itself.
We take a journey through space and time, from the beginning to the end of the universe itself. This is our world. Cities, forests, oceans, and people. Everything in the universe is made from matter created in the first seconds of the Big Bang. Every star, every planet, every atom, every blade of grass, every drop of water.
Water is ancient. The hydrogen atoms in here were born moments after the Big Bang. Then came everything else.
The Big Bang is the defining event of our universe and everything in it. The secrets of our past, our present, and our future are locked inside this one moment in time. To unlock the secrets of the Big Bang, we have to travel outside of our own solar system and journey beyond even our own galaxy. As we travel into deep space, we're actually seeing into the past and getting closer to being able to witness the dawn of time itself. Passing the first infant galaxies and the first stars, we arrive back at the moment the universe began and face the biggest questions in all of science.
This is the holy grail of physics. We want to know why it banged. We want to know what banged. We want to know what was there before the bang.
To get the answers, we've built machines the size of cities to simulate the conditions when the universe was created, as well as space telescopes to peer deep into our past.
We are getting close to answering the old 8 questions. Why are we here? Where did we come from? Does the universe, in fact, have a beginning or an end? And if so, what are they like? If we find the answer to that, it would be the ultimate triumph of human reason. We would know the mind of God.
The origin of the Big Bang is the greatest mystery of all time. And the more we learn, the deeper the mystery becomes.
We like to think that our universe is unique. However, now we're not so sure. Perhaps there is a multiverse of universes.
Another possibility is that our Big Bang is just one of many Big Bangs. But it may be one of just an infinite number of universes. And there may be other regions in that infinite number of universes where a Big Bang is just happening today.
But there's only one universe we're sure of. And understanding this one is hard enough. Since the late 1920s, everything we know about how our universe works has been turned upside down.
It's important to realize how much our picture of the universe has changed in the last century. At the beginning of the 20th century, the conventional wisdom in science was that the universe was static and eternal.
In 1929, that all changed. At the Mount Wilson Observatory above Los Angeles, astronomer Edwin Hubble discovered that galaxies are not static in one place. Not only are they moving, but they're flying away from Earth at incredible speeds. And this was the first real evidence of the Big Bang.
All galaxies on average were moving away from us, and stranger still, those that were twice as far away were moving twice as fast. And those that were 3 times as far away were moving 3 times as fast, and so on. Everything was moving away from us.
It became known as Hubble's law. His discovery is still the starting point for exploration of the Big Bang.
What Hubble convincingly demonstrated by seeing the motion of those galaxies is that the universe is expanding.
Theoretically, an expanding universe must have started from a single point. So, by measuring how fast the universe is expanding, astronomers calculated backwards and worked out when it burst into life.
People ask the question, how do you know that the universe is 13.7 billion years old? I mean, smarty pants, you weren't there 13.7 billion years ago. Well, when you watch television on videotape, you hit the stop button when you see an explosion, and you could run it backwards and see when it actually took place. The same thing takes place with cosmology. We can run the videotape backwards and then calculate when it all came from a cosmic explosion.
You don't have to be an astronomer to look back in time. If you gaze up at the night sky, you're seeing stars that are millions of light years away, meaning it took the light from those stars millions of years to get here. So, if you look back far enough, you should be able to see the beginning of the universe. Named after the groundbreaking astronomer, the Hubble Space Telescope allows us to look deep into the universe, back in time, and closer to the moment of the Big Bang. But for scientists, winding back the clock to the Big Bang was only the first step.
When people first hear about the Big Bang Theory, they say, well, where did it take place? It took place over there, it took place over there. Where did it take place? Actually, it took place everywhere, because the universe itself was extremely small at that time.
These are some of the most abstract and difficult concepts there are. And this is another. What came before the Big Bang?
The philosophers in ancient times used to say, how could something arise from nothing? And what's amazing to me is that the laws of physics allow that to happen. And it means that our whole universe, everything we see, everything that matters to us today, could have arisen out of precisely nothing.
It's one of the biggest obstacles to understanding the Big Bang. First, you have to believe in the premise that something was created out of nothing.
It's impossible to describe the moment of creation in human language. All we know is that from what may have been nothing, we go to a state of almost infinite density and infinite temperature and infinite violence.
Understanding how nothing turned into something may be the greatest mystery of our universe. But if you understand that, you start to understand the Big Bang, when time and space began, and when a great big explosion created everything. At the dawn of time, the universe explodes into existence, from absolutely nothing into everything. But everything is actually a single point, infinitely small, unimaginably hot, a super-dense speck of pure energy.
The Big Bang was so immense that it brought into existence all of the mass and all of the energy contained in all of the 400 billion galaxies we see in our universe in a region smaller than the size of a single atom. The entire observable universe was a millionth of a centimeter across at that time. Everything was compressed into an incredibly hot, dense region.
It's not even matter yet, just a point of raging energy. It was the beginning of the universe and everything in it.
Everything was simple. All the forces that we know about today were one and the same. The universe was amorphous. It had no structure.
In that instant of creation, all the laws of physics, the very forces that engineer our universe, began to take shape. The first force to emerge was gravity. The fate of the universe, its size, structure, and everything in it, was decided in that moment. Carlos Frenk studies how gravity shaped the universe by creating artificial universes in this supercomputer. He gives each one a different amount of gravity. The first one he tried had too little, resulting in nothing.
Gravity, it has shaped our universe. Or if gravity was weaker than it is, we would have a very boring universe in which everything would be flying apart so fast that there would be no galaxies forming.
Next, he programmed a universe with too much gravity.
If gravity was stronger than we think it is, again, we'll end up with a failed universe. Everything will end up in black holes. It has to be just so. It has to be just right.
Luckily for us, the Big Bang got it just right. The perfect amount of gravity. In the turmoil of forces after gravity emerged, still a fraction of a second after the Big Bang, a shock wave of energy erupted and expanded the universe in all directions at incredible speed.
All of space expanded by an unbelievably large factor in a fraction of a second. We think that in less than a millionth of a millionth of a millionth of a millionth of a second, space expanded by a factor bigger than a million, 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 million times.
And that's faster than the speed of light. But doesn't that break one of the laws of physics?
Even school children know that, quote, you can't go faster than the speed of light. But actually, there's a loophole there. You see, nothing can go faster than light. Nothing being empty space.
This idea gives even the best minds in science a headache. But it's critical to understanding the early universe. Scientists think it took less than a millionth of a millionth of a millionth of a millionth of a second for the universe to expand from the size of an atom to a tennis ball. That may not sound like much, but it's like a golf ball expanding to the size of the Earth in the same amount of time. That means it was expanding faster than the speed of light.
So many things were happening so fast in the early universe because everything was so close together that we need a new unit of time to describe things.
It's called Planck time. To understand just how short a Planck time is, consider this. There are more units of Planck time in 1 second than all the seconds since the Big Bang. The calculation is mind-boggling. There are more than 31 million seconds in a year, and it's been 14 billion years since the Big Bang. So multiply 31,556,926 by 14 billion, and you end up with an absolutely huge number.
It's a time scale that's so small that all human intuition goes out the window. If we look at our watches and measure 1 second, we can ask how many Planck times is that? Well, it is a billion, 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 billion Planck times.
So, now the Big Bang is only a few Planck times old. And a fraction of a second later, the universe is so small it can fit in the palm of your hand. But in another tiny fraction of a second, it expands to the size of the Earth. Then, moving faster than the speed of light, it grows larger than our solar system. And it's still just a raging storm of superheated energy.
It'd be hotter and denser and more violent than anything that we can experience in the universe today. Even the interior of a star is calm and serene by comparison to the violence of the earliest moments of the Big Bang.
Temperatures were so hot that even the atoms of your body would disintegrate. So hot, in fact, that the atoms would be ripped apart.
They're trillions of degrees hot. But as the universe continues to expand, it also begins to cool. Dropping temperatures trigger the next stage in the universe's evolution. The raw energy of the explosion transforms into tiny subatomic particles. It's the first matter in the universe. This conversion of energy into matter was predicted by Albert Einstein years before anyone started talking about the Big Bang. It's the one scientific equation every schoolchild knows.
There is one very familiar formula, and that is E equals mc squared. It says something about the creation of the universe. It says even if the universe is created just out of pure energy, that because energy can be converted to matter and matter to energy, that you can get all of the stuff that we see in the universe from this pure energetic event.
Einstein's equation had a huge impact. It led to the first nuclear bombs. In a nuclear explosion, a small amount of matter is converted into an enormous amount of energy. As the universe was forming, the exact opposite happened. Pure energy transformed into particles of matter.
You don't need to create matter in the beginning, you just need energy. And energy alone can lead to the creation of an entire universe.
In just a fraction of a second after the Big Bang, the building blocks of our universe began to take shape. But this first matter is nothing like we see today.
The stuff of matter has been very different over the age of the universe. What we now think is normal matter was not at all normal in the earliest moments of the Big Bang.
That's because conditions were so extreme. There were no atoms yet. But there were tiny subatomic particles.
In the earliest moments of the Big Bang, the universe was so hot and dense, there were great amounts of energy. And so particles were being created all the time, and energy and matter were transferring back and forth in this hot, dense soup.
That earliest matter was too unstable to start forming the universe as we know it. Think of it like this. Imagine rush hour at Grand Central Station in New York City as that superheated early universe. The commuters racing through the main concourse are subatomic particles.
If you look at a crowd of people, a large crowd of people, they may appear random. That random quirky motion is very similar than what was happening to the particles in the universe in the earliest moments of the Big Bang.
The extreme temperature of the early universe energizes the subatomic particles. They appear, they disappear. They race around at incredible speeds. It's pure chaos.
It's like people. If they're excited and running around fast to catch trains at a train station, they'll be moving around quickly. But eventually they calm down and get slower. That's what's been happening to our universe in a sense. The particles are moving around very fast, and as the universe cools down, the particles move more slowly and in some sense less randomly.
As the universe cools, the particles stop changing back into energy. Now there are more and more subatomic particles, but it's still a hot, violent place. All this is happening in fractions of a second, too small to detect. But now the Big Bang is moving into a critical stage. A titanic battle between matter and the one thing that can destroy the universe before it even gets started. Antimatter. Everything in the universe is made from matter. From the smallest rock to the largest star. And all the matter there will ever be was created from the pure energy of the Big Bang. Einstein's equation, E equals mc squared, says that energy transforms into matter. But it was just a theory. Today, science is able to test that theory. This is CERN in Switzerland, home to the world's largest machine. It's the size of a city and engineered to recreate the conditions millionths of a second after the Big Bang.
If we want to probe ever smaller scales, paradoxically, we need an ever bigger machine. There's just no other way of doing it. So big machines means small physics, means early times, and therefore getting closer and closer to the origin of the universe itself.
This monster machine is called a collider. It's designed to take us back to those first fractions of a second after the Big Bang. It's a 3.8 meter wide, concrete-lined circular tunnel, 27 kilometers around. The collider makes tiny particles of matter smash into each other at almost the speed of light. For a split second, those collisions generate turbocharged energy, similar to the explosive force of the Big Bang. And then that pure energy, briefly, transforms into matter, just like it did nearly 14 billion years ago. But this huge machine needs an enormous detector to see these collisions.
This detector is 5 stories tall and weighs over 7,000 tons. And 7,000 tons, to give you a sense of perspective, is the weight of the Eiffel Tower.
But as big as it is, it can't see the actual particles of new matter. They're only present for just a split second and move so fast, it can only record their trails.
There's a lot of energy in these particles. They move very, very quickly, and so you need a very large amount of detector in order to be able to map the path of these particles very precisely. So the detector is so big because you need better resolution. It works exactly the same as a camera. The more pixels you have, the better the picture. It's exactly the same here. We just have a 5-story camera.
Scientists hope that it'll reveal just how energy transforms into matter. But not just any matter. The type of matter that emerged nearly 14 billion years ago, at the dawn of time itself. But the dawn of time was a critical moment in the birth of the universe, because pure energy also produced one of the most dangerous things in the universe: antimatter.
Antimatter is the mirror image of ordinary matter. However, matter has one charge, and antimatter has the opposite charge. If there was an anti-me made out of antimatter, that person in principle could look exactly like me. Same personality quirk, same everything, except of course when I decide to shake his hand, at that point we both would blow ourselves to smithereens in a gigantic nuclear explosion.
Matter with a positive charge clashes with antimatter with a negative charge. The fate of the universe hangs in the balance of this epic battle. Equal amounts of matter and antimatter will cancel each other out, and it's not good.
A universe with equal amounts of matter and antimatter is equivalent to a universe with no matter at all, because the matter and antimatter will annihilate back into pure radiation. And there'll be nothing interesting, no stars and galaxies and people in between.
It was a cosmic battle, and the side with the most forces would win. It was very close, but there was one winner.
For every billion particles of antimatter, there were 1,000,000,001 particles of matter. That was the moment of creation. The one extra particle of matter in each little volume survives enough to form all the matter we see in the stars and galaxies today.
One in a billion might not sound like much, but it's enough to build a universe.
We're the leftovers. So believe it or not, everything you see around you, the atoms of your body, the atoms of the stars, are nothing but leftovers. Leftovers from this ancient collision between matter and antimatter.
Could antimatter still exist?
In the laboratory today, we have created anti-atoms, anti-electrons going around anti-protons to create anti-hydrogen.
Antimatter by itself is quite harmless. It's only when it comes into contact with matter that the fireworks start. Give or take a couple of Planck times, the universe is nearly a second old, and still a very strange place. But matter has won the battle with antimatter. And now it's time to build the universe. It's still extremely hot and expanding incredibly fast.
When the universe was a second old, the particles in it were very different than the particles we see today. There were no atoms. Nothing that we recognize in the room around us today yet existed.
However, now all that begins to change. Temperatures continue to cool, and as the primitive particles keep slowing down, they start bonding together to form the atoms of the first elements. The first one to form is hydrogen. Then, over the next 3 minutes, the universe begins to create two more elements, helium and lithium.
It's really amazing to think about that in a period of 3 minutes, which is, say, the length of an average news story on television, the universe went from the Big Bang all the way to forming the light elements that would be the building blocks of everything we see. In that short period, we went from the creation of a universe to ultimately the creation of matter. We went from a universe that was infinitely small to a universe that was light years in size. In the first 3 minutes, essentially everything interesting that was going to happen in the universe happened.
However, you wouldn't have been able to see it.
When we look at the night sky, we can see literally billions of years into the past, and we think it's always been that way. Nope, not true. 380,000 years after the Big Bang, that's when the universe began to become transparent. But before then, it was milky.
There is a dark, milky soup of loose electrons. The young universe has to cool down enough for the electrons to slow down and stick to new atoms. It took a long time for all the hydrogen, helium, and lithium atoms in the universe to form. Scientists calculate it took 380,000 years for the electrons to slow down enough so that the universe could start mass-producing atoms. When that happens, the milky fog clears. The first light escapes and races across the universe. Nearly 14 billion years later, two young scientists in New Jersey pick it up by accident. In 1964, Arno Penzias and Robert Wilson were mapping radio signals across our galaxy. Everywhere they searched, they picked up a strange background hum. They first suspected their equipment. Pigeon droppings were on the antenna. Maybe these were causing the strange signal. But after cleaning the antenna, the mysterious hum remained.
Penzias delivered a talk at Princeton University. And according to lore, one person in the back said, either you have discovered the effects of bird droppings or the creation of the universe.
It was, in fact, the moment of creation, nearly 14 billion years ago, when those first atoms got their electrons. That's the moment when the Milky Cloud clears and the new universe comes into view for the first time. To capture better images of this critical event, NASA launched the Cosmic Observer Background Explorer satellite, or COBE. They pointed it out into space where it took the temperature of the universe. By measuring differences in temperature across space, they created the first map of our early universe.
We got gorgeous pictures, baby pictures of the infant universe when it was 380,000 years of age. But there were problems with it. The picture was very fuzzy. The COBE results were simply not good enough.
So NASA launched an even more advanced satellite, WMAP, the Wilkinson Microwave Anisotropy Probe. In 2001, David Spergel was part of the team searching for a clearer image of the early universe.
It was exciting to go to the Cape. It was one of these moments where we're sitting there watching this. I was there with my family, watching the rocket go off. And it was very exciting when within about a day, we were able to get our first signal from the satellite and know it was working and working properly.
This is the most detailed picture of the early universe ever taken. Just 380,000 years after the Big Bang. The red and yellow areas are warmer, the blue and green regions cooler. And those temperature differences are clues to the future structure of the universe.
We see tiny variations in temperature. Those tiny variations in temperature reflect small variations in density. This region has more matter, this region has less matter.
Like a blueprint for the construction of our universe, this image shows us where there's more matter and where there's less. Regions with no matter will become empty space. Areas with denser matter will become the construction sites of galaxies, stars, and planets.
These are the fluctuations that will grow to form galaxies. So if it wasn't for those little density fluctuations, you and I would not be here today.
Believe it or not, everything you see around you, the galaxies, the stars, even the atoms of your body, have a predecessor in the Big Bang itself. Our galaxy was a ripple. a tiny ripple on the surface of the Big Bang as it exploded out. And these tiny ripples gave birth to all the galactic clusters and things that we see around us.
Our universe is now 380,000 years old and trillions of kilometers across. Clouds of hydrogen and helium gas float through space. It'll take another 200 million years before those gases create the first stars.
These first stars ignited the universe into what must have been the most amazing firework. The universe went from the Dark Ages to an age of splendor when the first stars illuminated the gas and the universe began to glow in majestic fashion. I wish I'd been there.
It was like Christmas tree lights turning on. The universe began to light up in all directions until you formed the beautiful mosaic we now see today.
More and more stars begin to shine. 1 billion years after the Big Bang, the first galaxy forms. Over the next 8 billion years, many more take shape. Then, about 5 billion years ago, in a quiet corner of one of those galaxies, gravity begins to draw in dust and gas. Gradually, they clump together and give birth to a star, our sun. Nine billion years after the Big Bang, our tiny solar system springs to life, and with it, planet Earth. Everything there is exists because of the Big Bang, and it's still going on. Our universe is still expanding. But it won't just keep going forever. Our universe had a beginning, and it will also have an end. In the 14 billion years since the Big Bang, galaxies have been created, filled with stars, planets, and moons. And the universe has been expanding the whole time.
We've learned space is quite big, at least 150 billion light years across.
The universe may be infinite. It might literally go on forever.
The answer is there doesn't have to be anything. In principle, the universe could be infinite and there's no outside. Or it could be closed on itself. It could be such that if I looked far enough in that direction, I'd see the back of my head.
We may never know if the Big Bang produced a universe that goes on forever. But we do know that the Big Bang hasn't stopped yet.
The Big Bang is really continuing now. We're continuing to bang, if you want, in the sense that the expansion of the universe is continuing.
One of the most astounding discoveries in the last few years has been the realization that our universe is not slowing down like we once thought, but it's actually speeding up. It's accelerating. It's in a runaway mode. We now believe there's something called dark energy, the energy of nothing that is pushing the galaxies apart and is killing the universe.
We can't see this destructive force, and we have no idea why it exists. But it could mean the end of everything created in the Big Bang. If dark energy continues pushing the universe apart, our Milky Way galaxy could become a lonely outpost. 100 billion years from now, most of our galactic neighbors will be out of sight. Stars will burn out. Galaxies will grow dark. Even atoms will tear apart. The birth of the universe, the Big Bang, was over in a flash. But the death of our universe will take almost forever.
That great philosopher of the Western world, Woody Allen, once said, Eternity is an awful long time, especially toward the end.
Working out how our universe will end is as dark a mystery as the Big Bang. It could collapse back in on itself, like a balloon when the air is let out.
So would the universe end with a big crunch, a reverse of the Big Bang, or was it end by expanding out and becoming cold and dark? If you wish, would it end in fire or ice, or with a bang or a whimper?
If the universe collapses, it might trigger another Big Bang. Maybe that's already happened, and we're just one in a long line of universes.
Personally, I believe in continual genesis. That is, there's a never-ending process whereby universes collide, split apart, give birth to new universes, perhaps with the different laws of physics within each universe.
Maybe this isn't the first time it's happened. Maybe it's cyclic and it goes round and round again. Eventually we'll collapse and the whole thing will start over again.
One universe or many, they all start with a Big Bang.
Everything that makes us human, the atoms in our bodies, the jewelry we wear, all the things that lead to the tragedy of life and the beauty and the excitement, love, everything else, arose because of processes that happened 14 billion years ago. And if we really want to understand ourselves at some fundamental level, we really have to understand the Big Bang.
14 billion years ago, the Big Bang created time and space, our whole vast universe and everything in it, including us.
Some people ask the question, what's in it for me? The Big Bang gave us everything we see around us. The distribution of galaxies and stars. It set into motion the creation of elements that we see in the universe, and even the laws of physics themselves, we think, were born at the instant of creation.
Everything started with the Big Bang. One brief moment in time, 14 billion years ago, that contains the answers to our greatest questions about our past, our present, and our future. Each discovery brings us one step closer to understanding how the universe works.